In the previous video related to the chapter equilibrium, I believe we spoke about basically what the strength of acids and bases are. That was just a discussion and other overview of the Bronsted-Lowry theory of acids and bases, and if I'm not wrong, the other one. And I forgot what the other one is, which is great. I know it's been a long day. And I decided to shoot a video because why not? So in this video, we are going to be talking about ionization constant of water and its ionic product. And if you think I'm not, talking as loudly as usual, it's because it's almost 10 p.m. So yeah. So the ionization constant of water and its ionic product. So when we talk about that, think about this. First of all, when we had reactions in the presence of an acid, water tended to act as a base. In the presence of a base, water acted as an acid. So water has this very unique capability of acting as both an acid as well as a base depending on the conditions around it. Okay, so when you consider the dissociation of water, first of all, it's a weak electrolyte, so it does not undergo dissociation to a great extent. But when it does, it's basically when you have two molecules of water. Sorry. One of them we can consider an acid, the second one we consider a base. Okay, so it will give rise to a conjugate acid and a conjugate base. So it gives rise to H3O plus and OH minus. Okay, both of them. So this is going to be the conjugate acid and this is the conjugate base. Okay, we are just H3O plus because H plus and that will just combine with another water molecule to form the hydronium ion. So when we talk about the dissociation constant, that is Kw for this particular reaction would be concentration of H3O plus into concentration of OH minus whole divided by concentration of the water. Now, because we have two water molecules, right? So we have H2O squared. Now, I know that's not been mentioned, like the square is not mentioned in your textbook, but basically, since it's a pure liquid, the concentration of water can be considered to be 1. So, the dissociation constant Kw will be equal to H3O plus, concentration of H3O plus into concentration of OH minus. Okay, so the Kw is basically the ionic product of water, and also if you notice, basically it's the equilibrium constant of this particular reaction of the dissociation of water reaction. Now it's or the self-ionization according to textbook. So it is an equilibrium constant, so obviously when there is a change in temperature, the value of Kw will also change. Okay, so experimentally at 298 Kelvin, the value of the concentration of H plus was found to be 1.0 into 10 to the power minus 3 molar experimentally. So it was experimentally found out at 298 Kelvin, the concentration of hydrogen ions is so much. We know that when we have a water molecule dissociating, it gives us an equal number of, so a water molecule gives us equal number of H plus and OH minus ions, right? So it gives us equal number of that. So basically the concentration of H3O plus is equal to the concentration of OH minus. Okay, and this is equal to 1.0 into 10 to the power minus 3 molar. Okay, so this is, oh, it's actually 10 to the power minus 7. I'm sorry, I'm not wearing my glasses. So I could not see that properly. So 10 to the power minus 7 molar. So Kw, the value of Kw will be equal to this into this. So concentration of H3O plus into, I don't know why I started writing it again. You already know that. Concentration of, so it will be 1.0 into 10 to the power minus 7 molar into 1.0 into 10 to the power minus 7 molar. Okay, so it's basically that whole square. So we are left with 1 into 10 to the power minus 14 molar square. Okay, so this is the value of the dissociation constant at 298 Kelvin. Okay, we were given the experimentally, it was calculated, or the concentration of hydrogen ion, H plus ions was calculated to be 1.0 into 10 to the power minus 7 molar. And since a water molecule gives us equal number of H plus and OH minus ions, the number of H3O plus ions and the OH minus ions are going to be the same. So their concentrations are also going to be the same. So we just use that value and multiplied it. Okay, so this gives us the ionization, or the ionization constant of water at 298 Kelvin. Now, basically, we are next going to figure out what is the dissociation, what is the ratio between the dissociated and the undissociated water molecules. There is a point to this, I promise. So when we think about this, density of water is equal to 1000 grams per liter. And then we know that molar mass of water is 18 grams per mole. Now the molarity can be calculated as 1000, that is the density, 1000 grams per mole, grams per liter, divided by 18 grams per mole. Now gram and gram will get cancelled. Okay, so when you have this, when you have a fraction, gram divided by liter, whole divided by gram divided by mole, and my math teacher taught me this a long time ago. You have to do that and then you do that. So essentially the gram is going to be in the denominator, so you're going to be left with moles per liter. So that's essentially the molarity, right? So the molarity of water is going to be 55.55 grams per mole. Okay, now we know that the concentration, so the ratio between the dissociated and the undissociated water molecules will be, so we'll have the concentration of dissociated in the top divided by undissociated, right? So that is 1.0, because that's the concentration of the water, the H plus ions, and 10 to the power minus 7 molar divided by 55.55 molar, right? So this 2 can get cancelled, and then this ratio is going to be 1.8 into 10 to the power minus 9. So essentially what we're trying to get to after all of this math is the fact that water likes to stay as water. It does not like to be separated into H plus and OH minus ions. It prefers to be in the undissociated form over the dissociated form, which makes it a weak electrolyte. Okay, that also makes sense that we consider the concentration of water to be 1, because most of the water stays undissociated. Okay, now so the equilibrium is more towards this direction. It's more towards the water molecule. Now, obviously, we are going to be talking about the change in concentrations. So, you have a H3O plus ion and OH minus ion. When you have a neutral solution, that is, when you don't have an acid or a base added to it, the concentration of H3O plus will be equal to the concentration of OH minus ions. Okay, at neutral stage, you have the concentration of H plus and OH minus ion equal, so you have that, right? When you add an acid to this, okay, when you add an acid like HCl, so what will happen is you will have more of the H3O plus ions. Okay, so what will it want to do to make sure that we know that it prefers the undissociated, right? So what it'll do is more of the H3O plus ions will try to combine with the OH minus ions. This in turn will lead to a further decrease in the OH minus ion concentration. Again, I'll repeat. So when you add an acid to this mess, or to this solution, I mean water, you have H3O plus OH minus. So when you add the acid, you have the increase of H3O plus ions. So now what it will want to do, it wants to make sure that you come back to this water because you have the equilibrium. Basically, it's the equilibrium constant. So the ionization constant of water always wants to stay the same. So what it will do is, it will combine with the OH minus ions to make sure you have the value of Kw correct. Okay, so what will happen is, at that point in time, the concentration of H3O plus ions will be greater than concentration of OH minus ions. It's not just because we are adding an acid, it's also because it prefers to make sure that it combines with this to make sure the Kw value stays constant. And remember, it's a constant, right? So we'll try to do that, and we'll go back to the to try and get to the water stage, and we can calculate the value of concentration of OH minus, as concentration of OH minus ions will be equal to concentration of Kw divided by concentration of H3O plus. Now, obviously, the same thing happens when you add a base. When you add a base, there is an increase in the OH minus ion concentration. So, when that happens, it tries to combine with more of H3O plus ions, so it can move back here so that the value of Kw stays constant. So, because of that, in the end, you'll be left with less H3O plus ions than the OH minus ions. So when you have the number of ions of H3O plus being equal to OH minus, that's a neutral condition. When H3O plus is greater than OH minus ions, it's an acidic condition. And when H3O plus is less than OH minus, it is a basic condition. So ionization constant of water and its ionic product basically gave us an understanding of what happens when water undergoes self-ionization. First of all, we spoke about the ionization constant, which is Kw, which is equal to the concentration of H3O plus ions into the concentration of OH minus ions. Experimentally, we were able to calculate that the concentration of H plus ions is 1.0 into 10 to the power minus 7 molar. And then we then use this equation to calculate Kw, because the concentration of H3O plus is equal to the concentration of OH minus. Okay, now, and then we were able to figure out that dissociated, in terms of dissociated versus undissociated, water prefers to chill in the undissociated form. So when we add an acid or a base to the solution, based on the, so if you're adding an acid, what it tries to do is the value of this will go up, right? So when that goes up, what it tries to do, it tries to combine with more of the OH minus ions to make sure Kw stays the same way. And in the end, you'll have more H3O plus ions than OH minus ions. And in case of the base, when you add a base, what it tries to do is it combines more of the OH minus ions combined with the H3O plus to lead to the formation of water. That makes sure Kw stays the same. But in the end, you're left with more amount of OH minus ions. With that, we're done with this very long name topic. In the next video related to equilibrium, we will be talking about the pH scale. Definitely, comment or write suggestions if you have any, or let me know if you have any questions, and I hope all of this made sense.